In this video, we will address how systems of inequalities apply to business applications. This is a pretty complex video, so you may want to watch this one a couple of times. Okay, so before we can even get started into the word problems, I have to give you guys some warm-up vocabulary. And that vocabulary is going to be on constraints and objectives. Okay, so it's important for us to understand both the concepts of constraints and objectives, and then when we get into word problems, we'll talk about where to find each one and what we're supposed to do with each one. Okay, so if you watched the video on systems of inequalities, you saw me graphing a bunch of regions that expressed how systems of inequalities interact. That speaks to the constraints. Those are known as the constraints. Okay, so the constraints is a set of linear, for you guys, linear inequalities. And what it does is it represents a region of feasibility. Represents a region of feasibility. Okay? So I won't give you a concrete example because that would take too long, but go back to the other video to see some examples of, for instance, when we had two lines like this interacting in the plane, and let's say that in this case both of the inequalities were of the less than type, so that we had this shaded region defined by a set of inequalities. Okay, so in order to get this shaded region, we would have that y is greater than 0, x is greater than 0, and then we would have two other lines defined, and the inequalities would both be of the less than variety. Okay, so inside this region, this shaded region here, we're going to call this the region of feasibility. Okay, because when we get into the word problems, you're going to see that this region represents the things that under a different set of, under various set of constraints, these are the places that I could be, okay? So these are the things that I could do in my business given the fact that I'm constrained by how much money I have to spend, how many work hours I have, or other different constraints. These are the possible things I could do. And when I say these are the possible things you could do, I mean like you could have x equal to here and y equal to there, or you could be at this point. You could be at any point inside of this region, or if there was an equals to attached to the inequality, you could be on any of the points lying on the line. Those are the possibilities. These are your possibilities. Possibilities under the given constraints. Okay, inside this region. Okay, so that's one thing that we're going to set up, and when you're inside a word problem looking for the constraint, remember that the constraint is a set of linear inequalities. Okay, so we'll try to extract that from the word problem, and when we do get a statement of a bunch of different inequalities, we will graph the shaded region, and we will know these are the possible things that I can do. Okay? And then I have to make a decision for my business, which one of these things should I do? And that's related to the objective. So the objective is going to be a function of two variables, because we're working inside two variable plane right now, that we wish to optimize. And remember that the keyword optimize means that we can either minimize or maximize it. Okay, so like some rough examples of this before we get into the concrete word problems. Let's say that we're restricted in the number of hours that we can, say, go outside and plant our crops. And we're also restricted in the number of hours that we can process our crops. Those are two different things that we have to do. And because we're constrained to this region, we could do like this much planting and that much processing, or vice versa, or whatever. But maybe I have something I want to optimize. In the instance of maximization, perhaps you're getting a certain number of, a certain amount of profit from all the different crops, and you want to get your maximum profit. Another thing that you might want to optimize in the minimization sense is that maybe you're the one who has to hire all the people who have to plant the crops and harvest the crops. And both of those jobs cost different amounts of money, and so you'd want to minimize the amount of money that you have to pay out to the workers in order to get a certain amount of jobs done. Okay, so we're going to be inside these word problems looking for two concepts here. Constraints, which tells us that we can only do a certain amount of stuff, or we want to do at least some amount of stuff. Those will be inequalities that we're searching for. And then we're going to be looking for the statement of some sort of function. And that function will depend on two variables, the x variable here and the y variable. And we will also want to know, do we want to minimize that function or maximize that function? So usually this is like some sort of cost or profit type of function that we want to optimize. Okay, so we have one more key component. The key thing about linear inequalities is that optimization of the objective function always occurs. Where does it occur inside this region of feasibility? At the corners. At the special corners. That's why we spend so much time to graph the shaded region and figure out the XY location of the corners, because whether we want to optimize, whether we want to minimize or maximize our objective function, it turns out that optimization of the objective function will always occur at these special places we found known as the corners. Okay, so there's a lot of black on here. It might be kind of hard to see what I want, see what I'm saying here. So now let's start in with the concrete examples. Okay, so we will have to deal with this in a word problem sense, but before we begin, I will just give you a little bit of a concrete example of what I meant here by the fact that optimization of the objective function always occurs at the corners, okay? So I'm already going to set you up with an example that's already about halfway done. Let's say that we've already given a set of inequalities, graphed the inequalities in the xy plane, and located all of the corners, okay? So this is already inside some sort of word problem. We found a set of inequalities. That set of inequalities told us that we have to stay inside this shaded region, and that shaded region is bounded by four corners whose xy coordinates I've listed here, okay? We have that information, and that is the information of the constraints. Okay, we're constrained, we're stuck inside this region of possibilities. And then we also have an objective, and the objective is known as the objective function. Okay, and that's going to be a function of x and y. So let's say that our function here, we'll call it c of x and y, is equal to 4x plus 3y. Okay, so what does that mean? There's a lot of maths to take in. What I'm saying is this is a function that I'm interested in knowing the value of, the output of, whether this is my cost or my profit or what have you. These are the different places that I could evaluate that function in a two-dimensional plane. Really, if I wanted to plot this function, because this function depends on two variables, I would have to go out to 3D, three-dimensional space, and then I could see what is the value of c at any one of these points on my function. Okay, that's beyond the scope of this class. We're not going to cover three-dimensional graphing here. But the key thing to know is that if I'm interested in either the maximum or the minimum, it doesn't matter which one. If I want to optimize this function right here, the optimization will always occur at the corners. Okay? So whether I want to minimize or maximize it, all I have to do is evaluate it on each of the four corners, and then I will find the place where there's a minimum value of c, and I'll also find the place where there's a maximum value of c. And that is really important for the decision making that I need to do inside this whole region of possibilities. It's a great thing to know that this always occurs at the corners, because you can see there's so many different possibilities on the inside. It would be really hard for me to choose. Should I go here? Should I go here? Which one should I pick? I don't have to pick from all of them. I just have to evaluate all the corners, and then I'm good to go. All right, so let's go into a little bit of evaluation of this function. Okay, so in this class so far you have not evaluated a two-dimensional function, a function of two variables. So we'll go through that very slowly. we want to do this at each one of the four corners, okay? So let's first evaluate the function c at the corner 0, 0. That means that x is equal to 0 and y is equal to 0, and so the value I get is absolutely 0. Okay, the next thing I want to do is evaluate it at, let's say, this corner, 0, 3. That means the x is equal to 0, and that means the y is equal to 3, and so I get 9. All right, 2 more to go. I want to evaluate this at 4, 0. I get 4 times x, which is equal to 4, and 3 times 0, which is 0, and so I get 16. And then finally I have my special corner over here, my 2, 2 corner, and that's when I have 4 times the x value of 2 plus 3 times the y value of 2, and that's going to be 8 plus 6, and that's going to be 14. Alright, so at each one of these corners, when I plug in both the x and the y value into my objective function, I see that the output from my objective function is given by one value. And let's say that I wanted to minimize this value. Right here, this would be the minimum value. Okay, so then I would choose x equals 0 and y equals 0 in order to minimize the value of that objective. If I wanted a maximum value, then I can see that the greatest output from all of these different corner choices, the best choice was 4, 0, in which I got the value of 16. So then I would know that this is the best choice for me if I wanted to maximize the output of my objective function. Okay, and the other thing that this star tells me right here is that I don't have to go in here and try all the other possibilities. Like for example, the point like 1, 2, that's, or 1, 1. Here's another point, 1, 1 inside there. Is that a minimum or a maximum point? Well, actually just roughly evaluating it, if I put 1 and 1 inside there, I would get 4 plus 3, which is 7. And you can see that amongst these values, 7 is neither a minimum nor a maximum. And so what that starts telling me is that I don't need to look anywhere inside here. Just on the corners will give me the minimums and they'll give me the maximums. That's pretty nice. It really cuts down on the work. Now we're going to go into the word problems, and you're going to see that these are quite complex problems here, where we have a lot of setup to do, and then we have to do all this graphing nonsense to locate the corners, and then we're going to have to evaluate an objective function at all the corners, and finally come about a solution for our problem. I'll give you a couple examples, and these are a bit wordy, so make sure you listen along with seeing what I write here, because I will not write everything that I say. Okay, so let's play pretend maybe I'm a baker. Okay, and Christmas time is coming up, and I want to be able to offer my customers some beautifully decorated baked goods that I've made in my factory. Okay, so I'm a baker, and I have 2 gift basket options. 2 different type of gift baskets that I make. I'm going to call number 1 my basic gift basket, and that takes me 1 hour to bake up everything that I'm going to put in it. And it also takes me 15 minutes to wrap it and decorate it into a nice pretty package to offer the customer. That's my basic package, and then I'm going to have another package, which I'm going to call my fancy package. The fancy package actually takes the same amount of time to bake as it does for the basic, but what makes it fancy is it looks a lot fancier, and so therefore it's going to take me a longer time to wrap that up, so it takes me 30 minutes to wrap up that fancy present to offer the customer. Okay, so these are things that we're going to use inside the word problem. We haven't really gotten there yet. Let's talk a little bit more about my business. How am I constrained as being the only baker inside my factory? Let's say that I have 10 hours of baking per day. That means that I'm able to, at most, and the keyword here is at most. Actually, let me rewrite that with the keyword in there. Okay, so I can bake for at most 10 hours per day. Okay, and then the other thing that I can do is I can wrap. I have to wrap those up, and I can wrap for at most, let's say, 4 hours per day. Okay, so you can see if I was the only one, that would be a 14-hour day. So maybe I do some of my wrapping while I'm baking, make it a 12-hour day. Anyway, the key word here is at most. This is the most amount of work that I'm willing to do in a day, and I can bake for 10 hours at most and wrap for 4 hours at most. And my question is basically overall, what should I do with my time? Like, how many basics of these should I make? How many fancies of these should I make? And really, the question is not properly posed now until I have an objective, some sort of goal that I want to reach, okay? So let's say that a goal, common goal for many businesses is the profit. Okay, so the profit is I'm going to make $30 for each basic gift package, and I'm going to profit of $50 for each fancy one. Okay, finally, the statement of the word problem is complete. Let's go over it again. So my basic package takes an hour to bake, 15 minutes to wrap. My fancy takes the same hour to bake, 30 minutes to wrap. I'm willing to at most bake for 10 hours a day. I'm willing to wrap for at most 4 hours a day. And this is the amount of profit that I make for each type. Okay, so just being a business-minded person like yourself, what do you think my overall question is going to be? Which is to say that, you know, every word problem starts out with a setup. What should I call my two variables here, x and y? Okay, so just take a guess at that. Pause the video and take a guess. Clearly write down what you would state as your x variable and your y variable. Okay, so I hope that you wrote down something like this. This is going to be the number of basics that I make, and y is going to be the number of fancy gifts that I make. And that's basically the decision I need to make for myself. How much time should I spend on basics? How much time on fancies? Knowing that I'm going to profit this much for each, but also knowing that I'm constrained by these things right here. Okay? So all this stuff right here is going to turn into our constraint. And down here, the profit, that's going to turn into our objective. Okay? Now, if you did set up with x equals the fancy and y equals the basic, that's not incorrect to do that, but you'll want to be consistent with what you see here, so go ahead and switch it to the same thing that I have here, just so you can work through the problem consistently with me. Okay, so now the next step is going to be write down my constraints. Constraints. And now I want you to practice this. Knowing that my x is the number of basics that I'm going to make, my y is the number of fancies I'm going to make. You see these keywords right here? Look for these in the word problems that you're doing. Keywords like at most or at least. Because at most is going to turn into this, okay? And then at least would turn into the other type of inequality. At most. So it means that I'm not willing to bake. I'm not willing to bake for more than 10 hours a day. I'm not willing to wrap for any more than 4 hours a day. And that's where those inequalities come in. Okay, so pause the video right now and use the x and y and the information on that board to try to write down what you think my equations inside here are going to be. Okay, so what I'm going to lay out now is how many hours am I baking? How many hours am I wrapping according to my plan of how many of each of these I plan on making. Okay, so the basic ones take me an hour to bake, so that's 1 times how many basic ones I made. The fancy ones also take me an hour, so that's 1 hour times the number of fancy ones I'm going to make. So you should get the inequality for the baking constraint that x plus y is less than or equal to 10. Okay? Now, if you didn't get anything here, go ahead and pause the video and try to write down the wrap one just for additional practice for yourself. Okay, so I'm at most willing to wrap for 4 hours a day. 15 minutes, watch out for your units here. Minutes is not the same as hours. So I have to transfer 15 minutes into 1/4 of an hour. And each one of those basic packages is going to take me 1/4 of an hour. 30 minutes is half an hour, so each one of the y's is going to take me half an hour. And so there you go. Now I've formed two linear inequalities, which I will seek to graph in the plane. And then also we have the very common and also implied. I didn't even say this, but this is implied. My x should be greater or equal to 0. My y should be greater or equal to 0. Remember those from the other part of the lecture? How many basics am I going to make? -2? Someone's going to come by and drop me off a couple? I wish. That's not going to happen. So usually the domain on word problems is that you're going to have non-negative numbers for your x and y. Okay, so we're not quite done. We're not able to apply the theory that you saw me apply on the example yet, because although we have constraints, which will define a region of feasibility in the plane, we do not have an objective yet. Okay, so the final piece of this puzzle is going to be to write down what is my objective, and that's going to be related to the profit. Okay, so without me saying any more, pause the video and write down the equation, a function of x and y that you think I will form right here, which represents the profit statement. Okay, so I'm going to make $30 off of each basic one, so that's 30 bucks of the x's. I make 50 off the y's, so that's 50 times the y, and I want to maximize this. Remember that in a type of problem like this, the objective function will either want to be maximized or minimized. It depends on the context, and here, if it's profit, yes, you're going to want to maximize that function. Wow, so now we have this entire setup, and we're going to take this math and apply what you saw me just do on the other example to this word problem. Okay? Geez, do you know what the first step's going to be? Yeah, that's right. We're going to have to graph all these inequalities in the plane, and we're going to have to locate the corners. Okay? So step 1 is graphing the region of feasibility. Graph the region of feasibility. That's that shaded region that you get from the inequalities. And locate all the corners, because you know the corners are the special places in which I will be able to optimize my objective function. Okay? And then the second step is actually going to be, number 2, optimize the objective function by evaluating it at each one of the corners. I can't really figure out what the corners are until I've actually taken the time to graph these two equations, okay? And so this one right here, x plus y, is less than or equal to 10. Remember, I want to solve that for y, so y is less than or equal to 10 minus x. Okay? Solve them both for y. So the next one is 0.25x plus 0.5y is less than or equal to 4. So I'm going to go ahead and solve that for y until I get y is less than or equal to 8 minus 0.5x. Okay? So these are really the forms. I didn't change anything about the inequalities except solving them for y. Those are the forms you're going to want to have it in before you attempt to graph it. Okay? Because that way, once you have it in that form, maybe I'll use a little color again. I'll use this one in red, and I'll do this one in blue. Okay, so my red one has a slope of -1 and a y-intercept of 10, which means it's going to go through 10 right here, and it's going to go through 10 down there. Okay, my other one has a y-intercept of 8, and it has a little bit of more relaxed slope like this. So really, its corners are going to be that the y-intercept is 8 right here, and then the x would need to go all the way out to 16 to hit 0 over there. Okay, I'm not going to need all those numbers that I just used, but that just goes back to how to graph the equation of a line. You kind of want to get an idea of what the y and x intercepts are, and then you just connect those in a straight line. That's how I'm graphing the line. Okay, but I have yet to shade in my region of feasibility. Should I shade this region or this triangle, that triangle? Should I shade up here? Pause the video and take a stab at it. Yeah, so I have both inequalities are in the less than form here, because I'm not willing to work any more than those two number of hours that I stated. And so if everything's less than, then I want to be below the blue line, and I want to be below the red line, and this is a region that describes a combination of both of those. Okay, now you can see how important it was to not only graph the two lines, but shade in the region of feasibility before I go to the place of locate the corners. If I had shaded this, then that would be a corner. If I had shaded this, then that would have counted as a corner. But because I shaded this, my four corners are 1, 2, 3, 4 corners of my region. How was I to know that without drawing it and shading it in? It's pretty hard to tell. Okay, so once you do that, you can kind of derive the equations of the corners, but some of them might be easy to see, like 0, 0, for instance, and then this one right here, x equals 10, y equals 0. This one over here is pretty easy. It says that x equals 0, y equals 8. This one's a little tricky. How are you going to get this one? That's right, you're going to solve this simultaneous system of equations, and I will just tell you the answer here, but I definitely want to recommend that you know how to solve these, so just pause the video, make sure that you can derive that the intersection point of those two lines is 4, 6. Okay? Alright, so now we have 4 corners, okay? So we have 4 corners, and that concludes step 1 of this 2-step process. Step 1, graph the region of feasibility and locate the corners. I got it. I got 4 corners. Now step 2, on to step 2, is going to be to finish my goal, which is that I want to maximize my profit function. So I'll leave that part up. Okay, so that's my goal here. And do I have to try out the infinite number of possibilities inside this region? No way, I'm not going to do all that. I will just evaluate on the corners. Step 2, evaluate your objective function at the corners, and then if you wish to minimize, you would take the corner that gives you the minimal output. If you wish to maximize, which is our case here, then you will take the corner which yields the maximal output of that function of 2 variables. Okay? So let's see, the corner 0, 0. What is the profit when x equals 0 and y equals 0? Well, I'm not going to make any profit there. Does something sound a little funny about that? Usually profit is negative when I evaluate here. So yeah, something's probably a little off here, because if I did have any fixed costs, I would still have to pay those out. Okay, so let's just roll with this for now, but I did think that's a little funny. Okay, so let's evaluate the other 3 corners. Let's say x equals 0 and y equals 8. That would be 30 times 0 plus 50 times 8. Okay, quick check of understanding right now. What am I talking about? What does it mean to be at the corner 0, 8? Do you know what that means? Okay, so going back to my definition, it seems like I've defined the y variable as the number of fancy packages I make. So what it's saying when you're evaluating this function at 0, 8 is that I have made the decision to make 0 basic packages and 8 fancy packages. That's what that means. And then the output of that function will be the profit. In this case, $400 is how much I will make if I decide to go that route. Okay? And then we can also interpret the point 10, 0. That means that I'm going to spend my day making this type of package, the basic package, and I'm not going to make any fancy packages. So then I'll make 30 bucks off of each of those 10, and I won't make any at the $50 level, so I'll only end up with $300, which is less than 400, so I probably shouldn't go that route. What if I make a little bit of a mix? What if I make 4 of the basics and 6 of the fancy? Then I'll get 30 bucks for each of those 4, and I'll get 50 bucks for each of those 6. So that's 120 bucks off the basics, 300 off of the fancies. So then I'm going to make 420, and that's going to be my best option, okay? Because this is the maximum value of my profit. And so my conclusion from this whole word problem, the setup was I'm in a baking business. I have all these different choices and different constraints and amount of money that I can make off each thing. This helps me make a conclusion. Amongst all the possible things I could do with my day, the answer is that I should spend my time making 4 basic and 6 fancy packages, and the result of that is that I'm going to yield a profit of $420 for that day's work. And I know because of the mathematical theory that that's my best option. I know it's not any smarter to just make the fancies or just make the basics. This exact mix is going to optimize my time and allow me to maximize my profit. So it's a lot of work, but that's a pretty powerful and useful statement for you. Okay, let's just do one more. These are going to be some pretty long problems this week, so I would recommend that if you are taking this online class, Math 147, please visit the discussion boards this week, okay? I want to see you guys making some good use of those discussion boards to help each other talk through the homework problems and figure out what's the setup, and then once you get the setup, what are you supposed to do with that? These are some pretty complex problems which you will have to address in a test-like setting, so work with your peers online. That will be great to see you guys doing that. Okay, let's just do one more example, and this time we're going to be an advertising company. Okay, and now we have a bunch of decisions to make in our advertising company, like I could run ads over the news shows, or I could run ads during sports shows. Some parts of my decision are I want to reach a certain amount of women and a certain amount of men because each of my products is targeted to those different gender groups. So let's just write down all the things that I know about my business right now, and then we'll discuss where to find your constraints and where to find your objective. Okay, so let's say that I run, in general, 1 minute ads. Okay, so when I refer to ads, each one of these ads is 1 minute in length. The news ads reach, remember my target demographic here is going to be between women or men. The news ads reach 7 million women, which I'll just write women. Okay, and they reach 4 million men. Alright, and then the sports ads, and I'm not trying to be gender biased or anything, but these are probably derived just by statistical data, is that when you run a sports ad, you're going to reach a different demographic, and you'll reach 2 million women that way, and you'll also reach 12 million men. Okay, so just by demographic observation and the statistical data, we know that if we run this type of ad, this is what we're going to hit for our target viewers. Sports ads will reach this many of each of the type of people, and then I have a goal. So my goal is I want to reach at least, let's say, 36 million women, and I want to reach at least 64 million men with all my advertising all together. Okay, so, wow, that's a lot of information so far. Let's kind of think about what we would want to use for our setup here, and what's going to turn into our constraints, and what's going to be our objective. And I'll tell you, for my objective, I have not written something on the board yet that will work as my objective. Okay, so let's just focus in on the top two parts here, and then we'll discuss objective. Setup. What I mean by setup is, what should I define as X and what should I define as Y? And I kind of want to do that as simultaneously as I consider the constraints, because knowing the constraints will help me decide what I should use for X and Y. Okay, can you see the constraints on there? Remember that the constraints will be expressed as inequalities, and the key words are either at least or at most. Okay, so you see it right there, right? You want to reach at least 36 million women and 64 million men. So I know that my constraint here on the number of women that I want to reach is going to be at least 36 million. Okay, so that's the number of women that I want to reach. The number of men that I want to reach, at least 64 million men. Take a look at this for a minute. This can be a little bit confusing. You saw in the last example, when I said at most, I put a less than. When I say at least, now I put a greater than. So that might seem a little bit opposite to you, but it actually does make sense, because when I say at least 36, I mean that 37 would be okay, and 38 and 39 would be okay, but like 20 would not be okay. So that's why it says greater than, because it has to be at least 36, so it has to be greater than or equal to 36. Okay, so I've already used those numbers. I'm still actually looking for some equations to put here, and I can't decide what equations I'm going to put yet until I decide what will my X and Y represent. Okay, so go ahead and take a minute to think about what would you put, and be very specific. What would you put for X and Y? Okay, so were you thinking maybe that X and Y should be the number of women and the number of men? Because I'll say that that's common, but that actually is misleading and that leads to mistakes. Whenever you see constraints here, you see the keyword at least and it says women and men, those are actually the things that you should not choose for the X and Y. Okay, because the numbers that come along with that type of wording are the numbers that go on the other side of the inequality. Okay, so last time you saw me say I wanted to work at most 10 hours of baking, at most 4 hours of wrapping, and the X and Y were not number of hours of baking and wrapping. Okay, so that is a theme of this type of word problem, is that when you see the keywords at least or at most, and those are attached to numbers for two concepts, those are not your X and Y variables. That's because those are the things that go on this side of the inequality. Okay, your X and Y variables are going to be something else that helps you to determine how much of these things that you're going to get. Okay, so what's your X and Y here? It's going to be the number of news ads you want to run and the number of sports ads you want to run, because if I name X as the number of news ads and Y as the number of sports ads, then I will be allowed, that will allow me to say, well, I know news ads reach this many women and men, sports reaches that many women and men. That will allow me to relate my X and Y to the numbers that I'm constrained by. So think about that with the last example too. I was at most willing to bake for 10 hours, at most willing to wrap for 4 hours. My X and Y were not baking and wrapping. They were how many of each type of package, basic or fancy, I should make such that I fit in the constraints. Okay, it's hard to search even for just the very setup. That's a very hard part of the word problem, but hopefully that hint will help you. And now that we've got this up there, now if you haven't already filled this in, go ahead and pause the video and fill in what equations you think I'm going to put here. Okay, you can see how important the setup is. If you don't get the setup of a word problem, you won't get to complete the word problem. You won't even have a fighting chance. So this is a very important part. Okay, so that 36 number, that was the number of women that I want to reach, and again, that's a hint that that should not be used as your X or Y variable. So taking the X and Y variable as the other double concept that I see here, I see that 7 million women are reached with each news ad, and 2 million women are reached with each sports ad. That's why I have 7x plus 2y is greater or equal to 36. Okay, 64, that's the number of millions of men I want to reach. And 4 million are reached with each news ad, and 12 million are reached with each sports ad. And there you go, that's the linear system. And once again, hidden inside here, implied, it wasn't even stated in the problem, but it's very much implied, is that the number of news ads I'm going to run and the number of sports ads are both greater or equal to 0. I'm not going to consider running a negative number of ads. It doesn't make sense, and it is not part of the domain and context of the problem. Okay, so this part's implied. This is the part you had to derive, and I hope you're starting to feel more comfortable with it. Start to read your book for even more examples of this, because just being able to see examples is what's going to help you to learn how to do it. Okay, so now looking back at what kind of setup I had so far, you can see that I've actually used everything on the board here, and like I said, I didn't give you an objective yet, but I kind of made one up. A common objective for me under this scenario would be that I want to reach my goal by hitting this many of each type of demographic, and I probably want to minimize my cost. Okay, so in the last problem you saw me trying to maximize my profit. Here I will try to minimize my cost. How much does a news ad cost? How much does a sports ad cost? I just made it up. Let's say that news ads cost like $300,000 per minute. I know those national ads probably cost a lot, so I made up these big numbers. Sports ads costing, let's say, $550,000 per minute. Okay? So now let's make up a function C of x and y, and we'll just keep the units as dollars, You could rewrite it in thousands of dollars or even hundreds of thousands of dollars or millions. But let's keep this just in the straight unit of dollars. What is my cost function as an expression of x and y? And you can see the variable definitions right there. Okay, so the function I'm going to be looking for here is that there's $300,000 cost times X news ads, and there's $550,000 of cost times each Y sports ad. So here's my objective function right here, and here's my constraints right here. These are my main constraints, and then of course I've got these two implied constraints, which are very common inside word problems. Whoa, there you have it. That's just the setup part. And now we have to go to the drawing board of that two-step process. The first step will be to use the constraints to graph a region of feasibility and locate the corners. The second thing will be the objective. We're going to evaluate the objective on each one of the corners that we find, and then we're going to pick out the minimum value. So, how's it going? Are you enjoying this? I hope that maybe you guys will use this someday. If you do use it, feel free to contact me by email or other method, because I love to hear about examples that students have actually done in real life here. Okay, so again, step one, graph the region of feasibility and locate the corners. Really, the corners are what we're after, but we're not going to be able to analyze that without a nice graph. Okay, so I want you to practice this by yourself, but really what I would do here is I would take this and I would solve each one of these for y in terms of x. Okay, so the top equation, this equation right here, becomes y is greater than or equal to 18 minus 7 over 2x. And the second equation right here turns into y is greater or equal to 16 over 3 minus x over 3. I want you to do this alongside with me on your page to make sure that you can do it as well. Okay, so the very preliminary step is rewrite these in terms of just y equals. And that allows us to make a nice graph, and you can see that let me use a color. I think that the color probably helps. Maybe just helping the boredom at least. Okay, so here's the red one, and here's a blue one. And the red one, you can see y-intercept is 18. The slope is negative 3.5. So that's what my red line is going to look like. This one has a y-intercept of 16/3, so a little bit over 5. And it's sloping a lot slower. Its slope is 1/3. So that's what that one's going to look like right there. Okay? And of course I could find the x and y intercepts for both lines and label them, and that's most likely how you would have drawn the line to any quantitatively accurate degree. Go ahead and find the shaded region now. Look at the inequalities and shade the region. Okay, this is different than the last time. The last time we had less thans, and if they were both less thans, I would have shaded this. This time we have both greater than, so what did you shade? Hopefully you knew to shade this region right here, and that's when you're above the red line, and likewise you're above the blue line. That's going to be all these possibilities. Boy, there's a lot of possibilities there. That's not even what we call a bounded region, because you can see it extends off to infinity. Okay? So the thing is that if we want to minimize this function, the same starred fact holds true that the minimal value of c will be located at one of the corners. Okay? Actually, because this is an unbounded region, the maximum value of c, you can see that the cost, just by common sense, the cost will increase for the more and more ads you run. Well, if you're going to go crazy on it out here and run a ton of both types of ads, of course your cost is going to go through the roof. So it turns out that you do not have a maximum value for C because your region's unbounded. However, you still have a minimum value, and when you're trying to minimize on that unbounded region, the minimum value will still be located, surely enough, at one of the corners. Okay, and hopefully you can tell why these are the corners. There are other things that would have counted as the corners if I had a different shaded region. But with this shaded region, I have these three corners here, and I have them clearly marked. Go ahead and pause the video right now. and write the XY coordinates of all three corners. Test your ability. Okay, so now I'll write down the three corners that I got. This one was 16, 0. This one was 0, 18. And this one right here was 4, 4. Okay, so that's step 1 complete. I've graphed the region, I've located the corners. And step 2 is that I'm going to go ahead and evaluate that objective function on each one of the corners. And I will just take whatever's the lowest, because whatever's the lowest number right there is the number that allows me to reach my goal. I know I've reached at least this amount for each demographic, and I've minimized the cost to reach my goal. Okay, so I want to minimize this function. So let's say, what is C when I'm at the point 4, 4? Okay, so that's 300. What does it mean to be 4, 4? What does that mean? 4, 4. Oh, that means that I'm going to run 4 news ads and 4 sports ads. Okay, so remember what the X and Y mean. So if I ran 4 news ads at a cost of $300K per each, and then I'm going to run 4 sports ads at $550,000 per each, then the total cost to me there is going to be $3,400,000. That's a lot of money, but I'm a big advertising company, so I could afford to do that if I wanted. But what are some other things I could do? What does it mean to be 16-0? I'm just running what? Just running news ads. That's right. Sometimes you have to go back to your paper and look at, what did I call the X again? Oh yeah, that was the news ads. So the .16-0 would mean I'm just running news ads, and those are costing me $300,000 each, and I'd have to run 16 of those in order to reach my demographic goals, and that would cost me $4.8 million. I'd rather not do that because I know that there's a cheaper option right there. But my other choice, of course, would be 018, and that would be just running sports ads. I'd have to run 18 of those, and you don't even probably need to type this number out to know that this is going to be really expensive because the sports ad was the more expensive type of ad. Why would I need to run so many sports ads to reach my goal? And that was because I wasn't reaching that many women with the sports ads each. So that's why this number is so high. That's also why it's not a good choice, because look at that. It's almost $10 million. Okay, so if I want to minimize this, of course I want a minimal cost, and that will be of 3.4 million, and that will be when I run 4 news and 4 sports ads. Okay, so that's my nice conclusion right there, is that the minimal cost of reaching my demographic goals is going to be $3.4 million when I run 4 of each type of ad. That's a nice conclusion. At least I know which way to go before I start trying all of these infinite number of possibilities, right? So hopefully you see the value in that. And good luck on that homework this week. Remember, talk to your peers on the online discussion boards so that you guys can work together and get those problems tackled.